Hello, everybody. Welcome to the P2 Live Forum. We're back for our second event after a break for a while. And today, just to get us all on the same page, this is the second of the third presentations from JonnyMac. And John has spent a lot of time working with this next-gen HMI display. So if anyone's not sure what we're doing today, I'll just kind of give you a little picture if my cords will allow that. But we're using this display. Okay, and that's the latest code just now published by John. And we're using it on a P2. I'm using a P2 Edge. You could use any board, and I'm on a JonnyMac, as you can see. And what we're doing is we're controlling these NeoPixel displays. Okay, so I've also got a setup here, and I know what people are dealing with who will be running this today. It's actually a very easy setup. So that's our interface is this display and a propeller, P2, and then some NeoPixels. So for JonnyMac, if you could do some muting. Thanks, Stephen. Got it. JonnyMac has, yep.
Quick question. I think you gave the co-host to Michael Green in case he doesn't know.
Oh, okay, thanks. I'll move it off of you. All right, and check now.
Still looking. Yep, there we go.
Okay. We all know JonnyMac has a lot to say, and JonnyMac, for every word he says today, he's probably written an hour of code. All right, so there's a lot more behind the scenes here, and we want to keep John moving. Ask your questions in chat. Stephen or I will grab them, or you can unmute yourself and ask John, but we'll keep John going, keep him on track, and keep this moving along. And if you actually have the hardware and you want to hook it up, there are several resources you might like. I will paste those right now into the chat. Come back here. Thank you, Zoom bar. So there's a number of links for you. Okay. So before we turn to JonnyMac, we'll just breeze through the housekeeping today. We still got this bundle on some kind of sale if you want to grab one of those, and we're using these LEDs today, but as you just saw from mine, they're more like a bar, a strip. Doesn't matter, these are just WS211 or 12 LEDs. P2s, if you're still waiting for P1s, let's talk about that first. We are getting 20,000 coming into inventory shortly. In the next coming days, we have to test them, then they'll be available, all right? So we should have met all back orders momentarily. And the P2, we have plenty in stock and more coming if you're designing a product. All of our events are on parallax.com/events. Go here and check it out, and you'll see there are different tabs. You can click on P2 events or on education events or all of them. And it's good to know where you are and what you're looking for. So click on the P2 if you're here. And if you're an educator, then you can click on the educational events because we have a lot of those coming up. One of them is this Thursday with Andy. This is before we send teachers off on break. We're just going to get them fully charged for a good semester when they return. When we also come back, we'll have, well, next week we have a presentation. 1 week from now, then we'll take a little break. And when we return in January, we'll talk about the state of P2 docs, and Jeff will show us where he is. Good progress on this hardware today, and as a matter of fact, we seem to have chased out the gremlins out of the hardware. And mid to end, I guess, January 19th, we'll talk about this. And January 26th, Francesco's industrial controller. Someone asked if we'll have these in stock. Yeah, I'll try to get a few of these in stock for you, along with the add-on cards. And Eric Smith in February for educators, Arduino stuff. And oh, here's a big one. The Propeller tool. 1 week ago, we've added the floating point. Good job, Jeff. And there is a link to download that if somebody wants to get it. So I guess next will be the final debugging work from Chip, and we'll have that done in time for this presentation. More educational stuff. Stephen is here. He's going to update us on the P2. This is his cube with it all flattened out and under some level of control a few months ago. More educational stuff, more educational. And then around mid-March, we'll have a 2-session activity around the P2 Edge, how to design it into your product. And we'll be including all the PCB files and all the best practices. And we're actually going to make a board out of this presentation, a little kit, a P2 project board. And we'll talk about that at the second. And then on March 30th, Gavin, who's with us today, good to see you, Gavin, will give us an update on his book. He's been very busy at work, and we've been sorting through his plan for the spring semester. Good to see him. This event was canceled, but it was never really, I think, announced. That was our P2 Expo at Parallax. So not happening. Okay, before we turn to JonnyMac, I should say that John's code is lovely, and I've been working with it this morning. And when I say working with it, that's a very liberal term. I mean, pretty much loading and go. And I feel like I have a very spoiled, luxurious position when I work with John, because he works for thousands of hours and then he turns this code over and I just get to run it. And I think that's been my career with engineers, which is really lucky. And some of them take a long time, like Chip worked for 14 years on something once before I got to use it. So I'm very thankful for what John has done here, and encourage all of us to free JonnyMac, and you can make a donation to John like I'm going to do today for his work, to thank him, because truly he's given us a huge jumping off point with this kind of interface. And just to get ready for this presentation, it's like he's made a whole product out of this display. I mean, it is a whole product. It's a Christmas tree light controller, or whatever you want to use it for, adjust it for. So tons of work. And thanks, John, for working with such deadlines. And you set a good role model in that way for engineering. So John, I'll turn over to you and let you roar. So live from Hollywood, California, JonnyMac.
Thank you, Ken. Hello, everybody. I'm glad to see so many people back after the marathon we went through last week. So this week won't be so bad. We have a lot of work to do, though. This is there's some pretty crazy stuff going on, but fun. You know, I think Ken will attest to that. He got the code earlier probably than everybody else. So if you don't have it, I posted it about 20 minutes ago in the forum. There's a thread in the P2 forum called Getting Started with the NEXTION. Your interface should show you it's, you know, should float to the top, because I just posted new files there. In post number 2 are the files that you'll need for this week. So they're all the P2 files. We have 6 demo files, as Ken will also attest to. There was only going to be 5, but I scrambled and got 6 working at the last second. It's not perfect, number 6, but it's useful. And, you know, everything I do is very iterative, so you'll understand that in a moment. And then there's 2 NEXTION files. One is an update from the passcode project that we did last week, the one that looked like an iPhone thing where you could lock and unlock, because I learned a new trick this week. One of the things that I try to do every day is learn something a little bit new. And since this display is so interesting, and my friend John Huffman, who's here, in fact, he's right below me on my screen, and my friend Rick are using this. And then I don't know if he's here. My friend Josh called me one day and he said, yeah, you know, I might have to stop watching your presentations, because every time I watch one, I end up spending a lot of money. So it was a very nice kind of roundabout compliment. But Josh and I work for a laser tag company, and I have been putting effort into this because I have product ideas for laser tag. And Josh, now having seen that, because I talked to him a little bit about it, but you know, we take in most of our information through our eyes, right? And so once you see it, and now when you can play with it, it really becomes, I think the value comes out. You know, again, my friend John, he's doing quite a large project with this. So a lot of the tricks that I've learned with the NEXTION have been coming from helping John with his project. So again, we have a bunch to do today, but I hope it'll be fun. I expect it will. And as Ken indicated earlier, If you have a question on the topic at hand, please just jump in and ask. I don't want anybody to feel left behind. Or you can go through the chat. I guess Ken and Stephen are monitoring that. So thank you guys for that. So I don't miss any questions, because honestly, I never look at the chat, obviously, while I'm talking. And with that, are there any preliminaries before I turn on the presentation and go? Okay. All right, so I will share my screen if that's okay, Ken.
Yep. I'm curious if anyone has hardware, let us know in the chat. We'd like to know.
Hopefully everyone's seeing my presentation from PowerPoint. Okay, and I'll go ahead and put it in presentation mode. Where is that? I know it is. Okay, we know what we're doing here. This is just a point of clarification. Last week we had a little bit of a confusion, and I want to clarify that. So what we're talking about last week, this week, and next week is using the Propeller 2 with the thing you see on screen. This is a smartish LCD HMI from a company called NEXTION. So this particular one we're using is 480 by 320, a 16-bit color. And it's not a generic display like you would use with, say, a VGA driver. You can put text and graphics and things on there, but they tend to be pre-built. What's nice about this is it has a scripting language built in and widgets and objects so that you can create a functional HMI, which you'll remember from last week stands for human machine interface. So generally, we're going to use this kind of thing to control something else. And, and we can also get values. Now, for our project, at least this week, it's a pure input device. We're not, even though we're talking to the display, we're not putting any information on it. Next week, we're going to change that. But this week, it's a pure input. So you can see on the screen, there's sliders. There's what looks like radio buttons. There's some color patches. This is another slider. One of the things I am going to talk about as well is that you can, with a little bit of effort, like I did here, make really attractive displays. Now, I think this is attractive. You may differ, but that's okay. I like the way this looks. It just looks something more like a commercial product versus if you use their standard kind of widgets, then, they're not, well, they're dull. Let me just say that. They're dull and flat, and they don't look very exciting. So we're talking about this. If I happen to use the term mobile, I mean something that I can pick up and carry around. I'm not talking about a phone specifically. Okay, that got us into some trouble last week. So this is the topic at hand. Here's the things we're going to talk about today. Because we've been away for a long time and we have some newcomers, we're going to do a real quick review of the P2. We're going to talk about connections between the P2 and outside devices, specifically with serial, I2C, and then smart pixels, how they work. And then we're going to go back to the NEXTION and pick up where we talked, from some things we did last week. There is a feature that is part of the NEXTION that I finally sorted out this week called Touch Cap. And I'm going to show you that. The little passcode entry screen project, if you look in that folder, I just uploaded the whole folder. So yeah, there's this one new file in there. It's called Passcode TAC2. That is the same program. It just behaves differently using the touch cap object versus button objects. We're going to then talk about the pixel interface that you saw on my device a minute ago, and how to connect it to the P2 and make things work. So in the process, we're going to go through 6 demo programs today. Some of them we'll go through quickly because they are for review. But as I was talking to Ken earlier, and John, who I've known and worked with for a long time, and Josh, who I've known and worked with for a long time, I do things in a very iterative manner because I want to make sure that things are working here before I move here. If you don't check this, it could break, and over here becomes a really big mess. So sometimes that seems a little plodding, but what you end up with is a much stronger product in the end. All right, as Ken was saying, we're talking about the P2. This is a picture from Ken. Here is the JonnyMac that we're going to talk about this RTC today. We're going to because we're talking about I2C, and there's an EEPROM on here as well. We're going to talk about that. We're not going to use it very much other than to demo it. Next week, we'll fold it into the NEXTION. We don't have an LCD for this project because we've got that fancy new NEXTION display. All right, P1 and P2. And please don't be shy. Unmute yourself. If you've never programmed a P1 or a P2, please say so or identify yourself. Okay, no absolute newcomers. All right, then a lot of this will be very quick review. This is a table I had done up for a presentation over a year ago, and it just shows the differences between them. We, of course, are focusing on the P2, and these are conservative, some of the numbers. So, for example, Chip will say, no, John, you can run 350 megahertz, which you absolutely can run the P2 much faster than 300. I actually run my code at 200. That's a choice that I make. Just remember, the faster you run it, the more energy you're taking. The P2 will comfortably do 300. It will go faster, as many have attributed to. The RAM space has grown quite a lot. We go from 32 to 512. I'm very happy about that, especially for the laser tag projects. The storage now for our program goes from EEPROM to flash. There's two reasons: size and speed. And they're related, of course. You know, we had 32K in the Propeller 1. It doesn't take a lot of time to program, you know, a 32K EEPROM, but whenever you got 512K, I don't know that anybody makes an EEPROM that big. You'd probably have to bank them, and then it's a little slowish. Flash is very fast. Now, there is a tiny bit of a downside, is that we don't yet, that I'm aware of, have a nice flash driver, and you know that we can use, you know, any way that we want. Flash is a bit different. With an EEPROM, we can just write to any individual memory location willy-nilly without worrying what's already in it. The Flash, there's rules about that, so it's a little trickier to write. Thankfully, that EEPROM that we have, or sorry, that little RTC module that we're using on a project has an EEPROM on it. And so in next week, for saving our settings that we put together, so when we boot up, you know, the thing comes back where you left it. I'm going to use the EEPROM until we've sorted out a really nice flash driver that's just as easy to do. The cog RAM, so remember we have 8 cogs. I did already say that. The cog RAM in the P1 is 2K. It's 4K divided into 2 sections in the P2. We can execute the cog rather can run code out of the hub, which makes, then you can have essentially an unlimited assembly program. Is that right, Chip? With hub exec, it doesn't matter what the size of my assembly program is.
That's right.
Okay.
Well, if you run in the hub, you can take the whole 512K.
There you go. So this makes the compiler people really happy. Because now they can compile to straight assembly and not worry about size constraints or using something like LMM. IO pins have doubled. Now, the little asterisk I put on there is because there are IO pins on both propellers that have devoted functions. So you'll see, if you look in any of my objects, there's a section that are child objects. You'll see a section that says fixed IO pins. So you have 63 and 62, which are the programming and debug port. And then the next 4 down connect, they're the SPI pins for the flash chip. And with some monkey motion, you can flip 2 of the pins and also talk to an SD card. I've not done that, but there are boards that are hooked up that way. The great thing about the P2 is that we have analog capabilities built in, and it's analog in and out, and on any pin, you know, we can do that, and that's through the smart pins functions. The smart pins allow us to do things in the pin that we would normally have to use external circuitry or assembly code to do. So it's really a great thing. I like the P2 a lot. All right, so here we go. We have 8 cogs. They all run at the same time. You know, I get irritated at there are members of the staff of the magazine I used to write for that rhymes with nuts and bolts that say, oh no, they're just running into one at a time. No, they're not. They're all running at the same time. All the cogs have access to power, all the IO pins, and the system counter. In the P2, it's called CNT as a register. In the P1 rather. In the P2, we use a get count, the GET-CT, to grab that register. And in the P2, it's actually 64 bits. The cogs run PASM or PASM2. And so that's where the interpreter is. The interpreter is running in a cog and it's assembly. The great thing about, or one of the many great things about the P2 interpreter, the spin2 interpreter, is that we can stuff little chunks of assembly into the interpreter on the fly and run it as if it was always there. I use this very, very frequently where I don't want to have to instantiate a whole cog to do a small process. There's improved access to the hub. I'm trying to go quickly because we have so much. In the P1, only one cog at a time was connected to the hub. In the P2, all 8 are connected. And I have a diagram that is an update that of what Chip did. Adjacent cogs can share data together through the LUT, right? Chip, it's through the LUT there where they do the share. And we talked about earlier, this is called hub exec. The cog can run assembly code that is in the hub. So you can have assembly programs of any size.
Right, that's right, John.
Yeah. Here's an update of a diagram that I had last year. And this, Chip has a really cool animated version of this, but here's the thing to note. In the P2, once a cog, let's say a cog wants to write several values into the hub. Once it gets synchronization with its initial value, it can write on every clock cycle. So that this hub rotator, you know, this middle rotates around, and you'll see that it does that because of the way the RAM is organized in pages where the lower 3 bytes point to, bits rather, point to a page. So it's a little complicated, but here's the end for people who haven't heard me say this before. I took a very simple spin program and ran it on a P1 at 80 megahertz, which is kind of the standard P1 speed. I moved that code over to the P2, made whatever language adjustments that were necessary, but no efficiency changes, just the language naming conventions. I set the P2 to run also at 80 megahertz, and I measured speed differential between the two. The P2 running the same code at the same clock speed was 16 times faster than the P1. The reason for that is several layers. It starts with the processor, of course. In the P1, it takes 4 clock cycles rather per instruction. The P2 only takes 2. We have a much more efficient instruction set in the P1. There's about 70 assembly instructions. In the P2, it's about 350, which looks a little daunting at first. But once you start poking around in there, you find that a lot of the P2 instructions will take the place of 2, 3, sometimes even more P1 instructions. So I have found as I'm porting my P1 code to the P2, my assembly code sections are getting smaller because the P2 code is just more efficient. What was the other thing? Well, and then the hub access, sorry. So the hub access and the way that the interpreter is written, you know, adds that all up. So now, you know, again, that was same clock speed. You know, imagine now if you take a P1 program and you port it to the P2 and you know, in my case, for example, I was 80 megahertz on the P1. Now I'm 200 megahertz on the P2. Well, that's another 2.5x speed increase. So in fact, again, I was helping John over the weekend with one of his, you know, camera control things. And he has 16 channels of analog that he is using an external ADC because he already had that circuitry set up. And before we needed 2 cogs to be able to read the ADCs and do a running average. So we actually will take the last 4 readings from an ADC channel and average them, and that's what we send out. So what that does is it just allows the ADCs to be really clean, especially with the joysticks. And in the P2, that's all in one cog and runs much faster. It's lovely. Okay, for those of you, this is more of my proselytizing. When you're programming, start with a template. It will make your life a lot easier. And Jeff has built into the Propeller tool the ability to add a specific P1 template and a P2 template. If you don't have one, you're welcome to use mine. I make them available until you want to create your own, but it'll just make your life so much easier. When you're starting to put together a program, think about what you're wanting to do. I tend to build out the structure of a program with empty methods, just so that I can see where things are going to go. Then I code and test each method independently to the degree I can. There are some times where we have dependencies where you have to do more, but if I can test an independent method at one time, I'm happy to do that. This is my anal retentiveness. Now, if I showed you around my office, you'd think that that hurricane that ran through Arkansas came through my apartment. Well, it didn't. My desk is kind of artistic, say it that way. And but my code is really nice and tidy. For me, looking at that, and since I'm sharing my code with all of you and many other people, do that. So think about that. Just make your code easy on the eyes. Document as you go. This is a trick, and even I catch myself sometimes because I'm working really fast. Once I get into a flow and I understand what I want a system to do, I can code quickly. But make sure you're documenting things. Now, something I've said many times before is that choose variable names and your constant names that make the code self-documenting. Spin is a really nice language. It's small and it just makes sense. So once people see it and look at it, oh, wait, that's actually pretty easy. Yes, I go through this all the time with new people that, that think that nothing exists outside the Schmarshmino. And then they show them what's happening with the Propeller and they say, wow, that's really neat. And it's easy. So, perceptions are one of the things our community, the Propeller community, have to break down for the other guys, because they think when you hear 8 processors that must be difficult to deal with, when we all know for a fact that it's not. It's the way that it's been designed makes it really nice and easy to do. And, Ken will attest to this. I sent Ken 5 programs earlier and I said, I'm trying to get one more, but I got to test. And I will confess, and I'll show you, I actually pulled a feature out of program 6 that you got today because it wasn't working as nice as I wanted, but I wanted you to have that program. So test, and then send it out. If you look at my programs, they're all structured like this. This is how I organize things through the code. This is where having a template plays out. Set all that up, and the objects that you're going to use all the time. For example, I'm always using serial and a couple of other things. So they're built right into the templates. Make your life efficient. Okay, here are the protocols that we're going to talk about today. This is just a review, so I am going to go quickly, but because now we're getting into the technical stuff, if you have a question, just shout out. I'd rather you get what you need right now so that later you're not struggling. So asynchronous serial is the kind of serial that we use going, say, when we're downloading or we're doing debugging. And the reason we say asynchronous is because the transmit pin, for example, transmit from one device to the other is a signal. There's no associated clocking signal with it. And so what we have to do on both ends is they have to agree about timing. And that's what we call the baud rate. Now, there are some devices that can listen and do an auto baud thing where the transmitter, say, will send out a specific packet and the receiver will listen to that and then figure out what the baud rate is and set itself up. We're not going to do that. We're going to make things pretty clean and easy. Now, in the embedded microcontroller world, now most of the time we're just connected point to point, where transmit here goes to receive here, and then the transmit over here goes to the receive there. Very, very straightforward. But you can do on a single wire, and you can do things like the open and driven signaling, 4 different tricks. I'll show you that. But again, the key to understand is the serial is what we're using when we download. And when we talk to the NEXTION display, for example, we're using serial. So in TTL, which is our 0 to 3.3 or 0 to 5 volts, we're going to normally, well, let me say this. There's 2 modes that we worry about when we're connecting to things: true, which is the normal mode, and inverted. So true mode, the idle state or the resting state of the transmit line is high. So it's in the Propeller 2, it would be 3.3 volts. When we start a transmission, that line goes low. This is called the start bit. Now, after the start bit, and the width of that bit is determined by the baud rate. So after that bit, there's going to be 8 data bits. The level of the line for the data bits in true mode will be the level of the bit. So if you have a 0 bit, the line will be low. If you have a 1 bit, the line will be high. After those 8 bits, we're going to go back to the resting position for at least 1 period usually, and this is called a stop bit. There is a mode also called inverted where everything is flipped. So the resting state is ground, the start bit goes high, the data bits are inverted from what they are. So if you have a 0 data bit, you put a 1 on the line and vice versa. And then when you're finished, you go back to the resting state, which is going to be ground. Now, there are devices that work this way that we have to deal with. And the great thing about the Propeller is if you have a device that wants to run inverted mode, like I think the servos that we did for the RC transmitter, it used an inverted mode. With the Propeller in the pin configuration, we can toss an inverter into the pin without having to hook up any external circuitry. It's a really fantastic feature. So we can write our code per normal and then just say, oh, invert that pin, and everything else gets sorted out. It's really, really great. RS-232 levels we don't deal with much anymore, but they're at much higher voltages. And then occasionally you'll get parity requirements. So, oftentimes you'll have then 7 data bits and a parity bit. Again, we don't see that very often. Again, going back to the I wish I could remember the name of that protocol. The servo, Ken, S-Bus, thank you. Yeah, with those servos, that they used a parity bit. All right, serial on the P2. If we use spin 2, you can do that. So you can write serial code in spin, and you can actually get reasonable data rates going out. Coming in, it's a big problem though, because you have no buffering. You can have serial arrive whenever it wants. So it's not really practical to do it. If you're just shooting a small message, and it's just going out, no problem. With assembly, really easy, and it's very fast. You can do anything you want, and you can even do, half duplex on the same pin. With the smart pins, there's a little bit more work, but I should have actually edited this. It's getting easier as I'm more accustomed to using smart pins, and they can be screaming fast. And we usually will use smart pins with separate transmit and receive, but we can, and I had before I said, hey, don't do this. Well, I edited this over the weekend saying, yeah, you can do it. So for example, there is those of you that are into robots, I know Kevin, he probably knows what these are. There's a actuator called a Dynamixel. It's like a smart servo that has a very wide range, and it will read back its position and all kinds of other stuff. It uses half duplex, and I just wrote a driver because John wants to use the Dynamixel in one of his projects, and I'm using the smart pins, and I didn't have any trouble with it at all. So you can use smart pins with half duplex. You just have to be aware of reconfiguring the pin in between transmissions. It's not hard to do, and I got it working quite nicely. These are what those signals look like. So again, this is what we're normally going to see when we define the serial pin in true mode. The idle state, the resting state is going to be at, in our case, 3.3 volts. When we want to send a byte, then we take the line low, and this green dot indicates what's called the start bit. Now, this bit width is going to be dependent on our baud rate. And then you see here are data bits. So there's 7 data bits, and you notice they go low bit to high bit in their order going out. And then we have a stop bit. So the stop bit period allows us to offload what we just received into our buffer. So it is important to have that. The inverted mode you see is just exactly the opposite. Everything is inverted. So the start bit goes high, and then the data bits are inverted from what they are in the value that we're transmitting. Again, if you have this in the P2, it's really easy to deal with because we can tell the pin to invert the signal coming in, and everything from there looks like this. This is another way. Now, if you're coding your own serial stuff, which you don't have to in the P2 anymore with the smart pins, but if you were, what we tend to do is we wait for the start bit, and then we set a timer for 1.5 bit periods. That's why you notice that says 1.5, because what that does is that gets us out to what should be the middle of the first data bit, and then we can sample the bit and stuff it into a holding register, and then we do that 7 more times, but we're setting this bit period to 1. And then in the end, we can check to make sure that we went to the stop bit. Now, the smart pin does all of this for us. It's very nice. The only trick with the smart pins is that they always send out N81, and the 1 is a stop bit, 1 stop bit. If you wanted to add a little bit of padding between your bytes and send 2 stop bits, it's really easy to do in assembly. With the smart pins, there's a little monkey motion you have to do in the way that I've done it, unless Chip tells me there's a better way, is that I tell the smart pin I'm sending 9 bits, and I set that upper bit to a 1. So it creates a faux stop bit, if you will. And then that way I can get a little extra time in between so that the receiver has time to deal with that. On the receive side, it's not a problem. Okay. Here is a, for those that are new and experimenting, you can get, if you go to Amazon and you can look up logic analyzer, you can find a little tiny logic analyzer that looks like this and costs $12 and works reasonably well. And so you can then download a free program for whatever operating system you care, because it works across all, called PulseView, and it will capture your signals. And then built into PulseView are protocol decoders. So I told it I have a UART, and it shows me what's going on here. So I can actually see this. When I'm doing, if I had a device, I'm helping a friend who works in the IT world do some hardware hacking, and I showed him how to take signals from the device he's looking at into a propeller and read it, but he had no idea what the data rate was. So instead of guessing, we hooked this up so we could actually see the signals coming from the device. And once with that, we were able to figure out the baud rate. And then I wrote a little capture program for him for the P2. So now he has a capture system, so he can run things through. And this is something I had done for laser tag. I had a piece of PC software that I needed to figure out, and the source code was no longer available. So I used a P2 hooked into the system as a spy device, and I could see the transmissions going back and forth, and the P2 logged it all and gave me a report. This diagram, sorry, I'm looking for my water. It's for full duplex. Full duplex means we can talk and listen at the same time. right? In half duplex, only one side can talk. So in this case, the blue guy is talking to the pink lady. And in this case, she's responding back saying, yes, I'd like $1 million. Thank you very much. There, sometimes we'll connect microcontrollers together on a bus. This is an open drain or open collector half duplex bus. So only one device is going to talk at a time. And usually the protocol will include a message, some kind of addressing thing that will, so we can indicate which device that we want to talk to. But in this case, we're using a pull-up on the line to create the high voltage level instead of using a driven condition, because imagine if this device was writing a 1, so outputting through the output driver, 3.3 volts, and then this guy put out through its output driver ground. You'd have a short circuit. So in this open collector, open drain arrangement, the way that this works is when a device wants to send out a message, all it has to do is pull the line low when it wants to write a 0 bit, and it floats the pin when it wants to have a 1 bit, because this pull up to VCC will handle that 1 bit. And there's the language or the naming conventions inside the P2 are really nice, because you have pin high, pin low, and pin float. Pin float, is what releases that pin. So if you're having a bunch of devices that want to talk together over a short distance, that's a really good scheme. Over one wire. Okay, sorry, I kind of blew through that. Any questions on standard serial? We all use it all the time without thinking about it, because we're downloading to the Propeller. And if you open up a debug screen or sending stuff out or using the internal debug, that's all serial communication. Okay. I2C is another connection scheme that is a contraction for inter-integrated circuit. It was created by Philips, and the idea was so we could connect a bunch of chips on the board through 2 pins. Now, this is called a synchronous system because there's a data line and a clock line, and the clock line is used to synchronize the transmissions. So it is half duplex. It uses that open collector, open drain scheme that we just talked about. So on an I2C system, there are 2 pins. One's called SCL for the clock line. The other one's called SDA for the data line. Both of those will be pulled up to VCC. And so they're generally in the system as a single master. There are conventions for having multiple masters. I've not done that personally with the Propeller. I think a few other people have, but I've not needed it. In my case, the Propeller rules. It doesn't need anybody else telling it what to do. And it will talk to other chips. So for example, we're going to be using we're going to talk about today and demo today and then use next week, the real-time clock and the EEPROM that are on that module. Those use an I2C connection. There is a feature of I2C called clock stretch, where when the master is talking, if the slave, which we call those external device slaves, if that device is not ready or it needs extra time, it will hold the clock line low. Remember that clock should normally be pulled high if everybody releases the clock line. The external device can tell the master, hey, I'm not ready yet, by holding the clock line low. And I think I told this story. A bunch of us in the forums that normally use I2C, we said, yeah, nobody uses clock stretch, let's get rid of it. As soon as I did, my friend Casey sent me a device that he wanted to use that did implement clock stretch. So I ended up putting it back into my driver. So it's in the driver you have from me. It is slower than SPI, which we're not talking about. SPI is that connection that we use for the flash chip, but it uses fewer pins and connections because it's a bus. In I2C, there are 4 elements that make up all of the transactions. You just stack them all together. There's a start condition, which is at the beginning of a transaction. There are write and read elements within a transaction, and then a stop. So it's very simple. If you look in my I2C driver, you'll see it has these things. Now I have enhancements on these where I can do a block read and a block write, but you'll see that they're just bigger versions of write and read. These are the 4 elemental aspects of I2C. It's a very straightforward, simple communication scheme to handle, and useful because there's a gajillion I2C devices available to us. When you get into I2C, you'll often see transaction diagrams like this in documentation. This is from an EEPROM thing. So the beginning, this section is called the control byte, or you'll sometimes see it called slave ID, because this is the device we want to talk to. And then this section here, the addressing will be device dependent. In this case, with this particular EEPROM requires 12 bits. The EEPROM on the P1 has 2 address bytes like this as well. The other thing to notice is that, and this is important because we're often used to sending data little endian, but you'll notice with EEPROMs, they go big endian. So you have to be mindful of that in your driver. And so the nice thing about these kind of transaction diagrams is they make writing code very, very simple. I've got a whole bunch of things. And in fact, a special effects shop just called me the other day for a little movie project, and they wanted me to do some motion thing. And I was able to find a couple of chips really inexpensively that they're accelerometers. They use I2C, so I got a couple of different ones to see which one's going to work best for them. And I know I can talk over I2C without any problem at all. Here's an expansion of that slave address or slave ID or control byte. The upper 4 bits are going to be what the device is. So if you see 1010, it generally is a memory type thing. And then you can have up to 3 address bits. So in this case, I could have 8 of whatever these devices are. If it's an EEPROM, I could have 8 of them. Now, not all devices use the address bits, and some use them in a little different way. So you have to look at the documentation. This is something that I always say is, once you get a new part, the first thing you should do is download the documentation and save it in your project folder so that you have access to it, so that you understand how you're going to be dealing with this. So for example, the EEPROM on this clock module has an address. It's preset to address 7, so all of these bits are high. The RTC, on the other hand, has the slave ID has no ability to use address bits. The logic being, if you have a clock on the bus, you only need 1 clock on the bus. And so they don't allow you to have multiple clock chips on the same I2C bus. Here's a capture, again, using that pulse. And what I wanted to show you, this is an actual thing. This is how I figured out what was going on with Casey's little smart encoder, is that here I was requesting data from the device and it was stalling. And then once I looked at it, you see here's the start condition up here, and here I'm sending, the request. You see this low right here. This is the clock stretch. This is the external device holding the clock line low. Once that is released, then everything else takes off. So that's a real world clock stretch. It still makes me laugh because I think it was Peter Jakacki and Ray and I and a couple of other people saying, yeah, nobody uses clock stretch anymore. And then I ran headfirst into it. So here you can see the details of the thing. Now, interestingly, you'll notice that when you do a read from an I2C device, and I'll show you this in the EEPROM driver, you actually do a write, and you write the address you want to read from, the starting address, and then you restart the condition in read mode. So you can see here's an address write. So you notice that this bit is 0, and here's the same address, and the read bit is set to 1. So everything after that is going to be a read. So there's a couple little niggly rules, but they're easy. And there's that data that was coming back. Okay, questions on I2C? I know we're going very fast because we want to get to the fun stuff. Okay, either I'm muted or everybody else is. All right, we're going to talk about pixels. These fun things. I've got, see, they're dangling all over my desk. These guys, got them all lit up. Here, I'll do this now. See them going. Yeah, see, Ken's got some too. Now, the pixels that we're using that we got in the kits last year that look like small Christmas lights, those use a driver called the WS211. It's the original driver of all of these families of things. I may have told this story where about 10 years ago, maybe a little more, a guy that I work with named Mike Deek, who's he's a really great guy and a very smart effects guy. He's very practical. He knows how to make things work. He's the quintessential popsicle sticks and rubber bands guy in special effects. He can make things work because he spent a lot of years working on low budget monster movies, doing fantastic stuff with very little resources. Anyway, one day he nonchalantly says to me, "Hey, John, you know, we're always using LED strips. Does anybody make a strip where we can set the color of the LEDs independently?" And I said, "I don't know." And I think this is in 2008 and 2009. So it's way back. And I have a friend named Corey who imports, you know, ship container loads full of LEDs that he sells across the nation. I called him and he said, "Yeah, we just got this new thing called the WS2811." And he sent me a roll. And I actually tested the original one using a basic stamp because that particular, oh, sorry, that was a WS2801, excuse me, because it was a 2-wire system. This is why I was able to test it with a basic stamp, because it had a clock and a data pin. So there's synchronization there. The 2811 is the 1-wire version of that, which now we get into where we've got to have a reasonably fast processor to deal with it. Now, the Propeller never had any kinds of problems at all because we have very precise control with assembly in a cog. And the great thing about the Propeller as well is that we can devote a cog to run whatever device we want to run. This kind of goes to way back when, to the age of what we call virtual peripherals. You know, Ken and Chip will remember that with the SX days, we coded peripherals in an interrupt. Well, here we can put the peripheral in a cog. So we can be very, very precise. So the W82811, if you have these, you know, with the module on them, you can actually see it's a little 8-pin chip. It doesn't have the LEDs built in. The WS2812 has all of that integrated into a 50/50 LED with slightly different timing. There is another smart pixel that gets getting very popular, and with the people that I know in the movie business tend to use it a lot too. It's called an APA. Oh, I have a typo there. It's called an APA 102C. It uses 2 pins, so it's synchronous, and it's very fast. It also, this device internally has better PWM capability, but many of you heard me talk about my friend Rick. I mention him all the time. He's one of my best friends. He's you know, building robots and stuff, you know, for that TV show called The Mandalorian, the Disney Star Wars thing. So there are propellers being used in Star Wars. I can attest to that, and some of my code too. So that makes me happy. Anyway, Rick has got some stuff that he's doing on set now. Is using the Propeller and WS2812s. There are also things you'll see called SK68 and then a number. Some of those are 32 bits, so they have a white color channel. So most of them, we have the red, green, and blue. We have red, green, and blue channels. Some of the other varieties have red, green, blue, and white. Because, you know, theoretically, if you mix red, green, and blue together, you get white. But with LEDs and the chemistry and, you know, all that jazz, you never get a perfect white. So the LED manufacturers put a white chip into the thing. And now with just the extent of manufacturing, we have, especially again in the film industry, where we care about what's called the color temperature of the light. You know, there are even that is now we have warm LEDs. So it looks more like, indoor lighting or sunsetting. And then there's cooler light, like midday. We call that it's a bluish kind of cast to the light. Anyway, all of that stuff. All of these, the WS211 and 12, like what we're using, are asynchronous. This is synchronous. They're easy to run on the P1 or P2. These are the drivers that I have. We're going to be using this today. So it will handle any of the single wire pixels that are available. They all run identically, and they all have an 800 kilohertz bit rate. It's just the width of the bits internally that change. So there's a whole bunch of start methods that are built into that object so that you can accommodate any LED that you want. Here's an actual project with WS2812s. I think I showed this in another presentation. Those of you remember a few years ago when Stranger Things was very popular, my friend Matt, who in his youth was a sign painter, made a full-size set in his house of Stranger Things. And so these are holiday lights. They're Christmas lights from a company called Holiday Coro. And so he did a frame grab from the show, made this false wall. And then he invited people, anybody that came over. In fact, people from the TV show came to his house too, because this got such a lot of buzz in Southern California. And you'd sit there, be talking, and then this phone would ring. This is not his actual phone. It's a prop that looks like the one from the show. And when somebody picked it up, then all hell broke loose and the thing happened. And those that remember from the show, the kid that was lost in the other dimension used the Christmas lights to communicate with his mother. So Matt wanted to do that. So behind this wall is a P1 that has an RS-45 connector on it. And so Matt's show control software is sending commands over RS-45 to the P1, which is then controlling the fade off, fade back on of the lights and spelling words out. So it was really quite fun. I made a miniature version of this for trade shows, which people like. So this is fun stuff that can be had with it. This is what the data looks like. There's a lot coming out. So again, this is a capture from using Pulse View. Now here I've overlaid some colors onto it so you can see what's happening. Let's say we had 3 colors in our stream, red, green, and blue. So what you can see internally, there are 24 bits are transmitted for every pixel. And in the WS2811, we send out the red bits first, then the green bits, then the blue bits. So you can see if you look carefully, there are some wide bits in the red. All of these, oops, I'm gonna stop clicking on my mouse. All of these are skinny. By the same token, you go here where I shaded this green behind, you notice in the green section, there's some wide bits right there. And then in the blue, there's some wide bits right there. So it's really, really easy to deal with. Here are the timing requirements for the WS2811. The way that these things work, because you've got a whole bunch of these individual chips and you've got an input and an output. And what happens is that when the data line is quiet for 50 microseconds or longer, internally the chip resets itself. So it's looking at its input pin. So you send out the data from the controller and the first pixel in the string gets 24 bits. Once it has 24 bits, it flips a switch and it reroutes its input pin to its output pin. So the next 24 bits go to the second LED and so forth and so on. This is how the addressing works. It's automatic based on a switch internally. The other nice thing too is that there's some signal conditioning on the inside of the chip. So if you're a little ragged getting to the first chip, as long as you can get to the first pixel, everything downstream should be good because the signal is buffered and cleaned up on the way out. So my buddy Rick, because some of the pixels really 3.3 volts is a little bit on the ragged edge of the input requirement voltage, he'll just put a pixel on his board and use a pixel as a buffer. So pixel 0 is on his board and pixel 1 is the first thing that's in the object. But here's the timing. You'll notice this period is always 1.25 microseconds for 800 kilohertz. A 0-bit has a narrow pulse and a 1-bit has a wider pulse. So this is how we're, this is it's asynchronous serial, but done with bit width. The WS211B, which is the very popular version, it's like the strip Ken had, that's how you'll see them often. It looks identical, but if we get under the hood, then you'll see something critical here. Here's the red, I want the first thing to be red, but you'll notice with the WS2812, it sends out its green level first, and then it's red, and then it's blue. So the red and green are reversed from what we would normally think. So if you are running a project and you're trying to make something red and it's green or vice versa, change your driver. So if it is a WS2811, if you've told it that's what it is, change it to WS2812, because that's really the difference between the two, is that there's some small timing variations you can see here. All of this is the same. The 0 pulse and the 1 pulse in the WS2812 are a little wider. I think that's for reliability, but you can run WS2812s running the WS2811 driver. But again, if you say be red, it will be green and vice versa because of the byte order that the chip is expecting.
John, that must explain my red and green being switched in your demo, huh?
Yes, but we were talking about that and then got cut off. Yes, that's exactly why. So if it wants to be red and it's green, change the driver. Okay, for those of you playing along with hardware, this is my JonnyMac. I just photographed this about an hour ago. So here's the clock module. I'm using pins 0 and 1. You'll see this, these are defined in the code, but I just want to show you my setup that's controlling these things. These wires are to the NEXTION display. The yellow wire, which is the receive into the NEXTION, is connected to pin 8, and the blue wire, which is the transmit from the NEXTION, goes into pin 9. And then I'm grabbing 5 volts from this header here. Remember, the NEXTION is a 5-volt device. You gotta set it to 5 volts, but at least for the basic and the enhanced units, which is what we're using, the serial levels are 3.3 volts. There is another thing called the intelligent display that's got a red or orange PCB that uses 5-volt IO, so you need to put a resistor in for that. And then these wires are for my displays. I don't know if this will show up, but there's a black 3-pin connector on the wires. I just extended those out with male-female jumpers, and then there were 2 loose pigtails, and I just extended those with jumpers as well. So you'll notice I've got 2 reds and 2 blues here. So the reds are 5 volts and the blues are ground. And I put them over here on this servo port because there's this buffer capacitor right there. So since these can take a bit of current, now make sure that when you're running these things, you've got a beefy power supply. I've got a big 5-amp, 5-volt power supply plugged into my JonnyMac, so I can run these as bright as I want without any problems. But this is what my board looks hooked up, and I've tested all the programs we're running today with these connection and verified that it works. Any hookup questions? There's a bit of debris right there. I don't know what that is. Okay. Nobody has any questions at all. I'm that good. Sorry, little cheeky today.
And John, it's quieted the chat as well.
Okay. All right. Well, then let's look at some Propeller code. I'm trying to figure out the best order I want to go in. Yeah, let's look at Propeller code since we just talked about those protocols. So if you have them, there are 6 programs that I made available today. The first one is an I2C scanner. This is the same program that we used last year. I just made a new copy of it and hooked up for here. This is a useful tool that I use all the time. So for example, when I look at these guys, I will hook them in and I will run this program because it will show me what their addresses are. So the purpose of this program, and I might as well just be quiet and run it. The purpose of this program is to look at the I2C bus and tell you what's there. Can everybody see my PST window?
Yep.
So it went through and scanned the available addresses on the bus, and there are two things. This AE, that is my EEPROM that is on the clock module. And so now I know that those 3 data bits that are on the EEPROM are pulled high, because that's why I've got those bits high. And you can see that here. Here's I've kind of broken it so you can see here's the device type, here are the address bits, and then these are the read write. That's the read write bit. So for those of you that have done I2C in the Arduino world, they use just the 7 bits. So if you're porting Arduino code to the Propeller using my driver, I'm using the 8-bit style. So just take whatever your address is and shift it by 1. The Arduino does that internally. You'll want to do that externally with my driver. Okay, so 2 devices. And so there's our EEPROM and there is our clock. So speaking of clock, we'll run it again. So here is a very simple clock demo, and I'll actually go through the code on this one. The EEPROM is, or sorry, the I2C devices thing, you know how the protocol works. So we'll actually look what we're doing. This particular clock, the DS3231, has temperature built into it as well. So it's a very convenient little dude. I had this same module from last year with a battery in it, and the clock was off by an hour. I don't know why it was off exactly an hour, because it seems like it should have been close because of daylight saving times, but who knows? I've reset it, so it's correct now.
Hey, John, I suspect you have, I suspect both those temperatures aren't centigrade.
Oh, thank you for fixing it. Well, okay, so everybody go in and, yeah, here's an easy fix. Thank you very much.
You're welcome.
I looked right at that last night and didn't even see it. Because I didn't have Fahrenheit on there last night. I decided to put it on. So thank you for that, Stephen. Anyway, easy fix. And so on this, if we look at the object, there is an object for the real-time clock, and it is a parent of the generic I2C object. So if we look at that first, here's the I2C object. Now, because there are of those pull-ups that are out on the I2C bus, you can configure them in a variety of ways. So note to those that are already using my I2C driver, I added this constant name called PU_EXT for external, because I had none, and that meant, okay, we're using an external thing, but it seemed like it could confuse people, like, okay, we don't need pull-ups. So it's the same thing. We're not using internal pull-ups because we're expecting them external. So this is a purely cosmetic thing to prevent confusion. But if we look, hang on, I'm gonna move these control things around. If we look at the summary view, here is there's the start, write, read, and stop. Those are the basics. Everything else is built on that for convenience, but those are the basics of the I2C command set. So it's really very straightforward. And again, when you look at a transaction diagram that you'll find in the documentation, you can just use these things. Now, if you want to read a block of bytes, like if you're reading a big chunk of memory or writing a big chunk of memory, then you can use the write block and read block commands, because they'll take care of incrementing the addresses. Now, since this is kind of a black box, you know, what I decided to do for best speed and precision, this is that feature I was talking about for those of you new to the P2, where I can use assembly language in the middle of my spin program. And so this is called inline assembly. And I really like doing this. So you see this whole program is, the shells, if you will, are in spin. All the code is in assembly. So it runs really, really efficiency. And I have very tight control over the bit timing. That's why I did it that way. If I didn't care about the bit timing, I'd have done it purely in spin. All right, going back to the clock. Now the clock has all the kinds of things that you would expect. Sorry, so if you ever go to summary mode and you get a bunch of weird background stuff, just go back to full source and go back to summary. I've talked to Jeff about this. We don't know why it's happening. The one thing to note about the RTCs is they have these registers in them, and they run in BCD mode. That stands for binary coded decimal. And here's the nice thing about it. If we take a BCD value and we say, hey, show that as a hex value on the screen, it will look correct. So in BCD, it's treated, it's like a hex, but we don't use the A, B, C, D, and E through F values. And we only, for each nibble, we only can go 0 to 9. I guess that's the best way to put it. So you can see that in the demo, when we're, well, here's one of the things that I did. Now you'll notice this instantiates all the objects for the program, and I have this commented out. It says initialize RTC, but what I did, this is what allowed me to set up the registers, so I could program the clock. Since it has a battery in it, I only need to do this once. But you'll notice, so I'm setting my seconds to 0, and I'm setting the minutes to 30. And so this is 30 in BCD. And then it was 5 o'clock when I was doing this. So it was 1700. I always use these clocks in 24-hour mode. They have 12-hour modes in them, but it's always funky to work with. So for me, excuse me, I find it easier to just work with it in 24-hour mode and then have my program deal with the hours. If it's 0, I know it's 12 midnight, and from 13 to 23, I know it's PM. It's just much easier to deal with in the high level code. So if we, now I was wondering why I'm not showing here. So I have a built-in function in the program that says AM, PM. So if I look over in the in this module, there it is. Here's my time string, and it's taking care of putting those values into a string. But for quick and easy things, you can display in hex. And it will show you, in fact, watch, I'll just for grins, I will, since I have the registers here, I can, and I have formatting in my serial. So by doing 0.2x, that will give me 2 digits in hex format. And then I will do hour min. Now, it's always dangerous doing live demos, so hopefully this doesn't bite me. And it did. Is it 2:14? Yes, okay. I was wondering why I was getting 14:14. It's because it's 2 p.m. But here you can see that I'm running the clock. Now this is 24-hour mode because I didn't do the conversion. but it's because I'm treating those values as hex. So bear that in mind when you're doing displays. It's pretty easy to deal with writing the registers directly. Okay, and so since with this particular clock, we have features built in for reading the temperatures. So pretty straightforward. I won't belabor this. We're going to talk more about this next week when we put it to use. Excuse me. All right, the next program accesses the EEPROM that is on that same module. And we look at this, this will show you what a blank EEPROM looks like. When a EEPROM is erased, it's all Fs, everything. So that's one thing to know. And you can use that to check as a flag. If you have a new product, say, and you want to know if things have been initialized, you can put, your program can assume there should be a non-FF value in a specific spot in the EEPROM, so that when you start up, you look for that. And if it's FF, then you know it hasn't been initialized and you can set it up. So here I've written some a byte, a word, a long, and a string into this EEPROM, and then you know, spit that range of values back out. But I want to show you, so this is pretty easy. 0 is 0. For those, you know, we throw around terms like little endian and big endian all the time, but this lets you see it because these addresses are going, you know, they're ascending, going that direction. So here the value is hex 1234, but you notice that the low byte comes first here. So this is showing us little endian. Same with the long. Notice how the bytes are reversed from what it appears, but that's because this is the low byte and this is the low address. You can see that. And then the string does go in order. The thing to remember about strings, which is very important, is that they need to be terminated with a 0. All the string functions that we use expect a 0 to be on the end of that. Sorry, my LEDs are actually becoming quite warm. So easy peasy, we can read and write to an EEPROM. The nice thing about the EEPROM is that we can write to individual cells without caring what's in there. We are not able to do that with a flash until we get a flash driver. And I'm going to ask if he's still here. If Mike Green is still there, did you not do a flash driver using some spy code that I wrote?
Sorry. Yes, I did.
Because I thought you'd send it to me and I couldn't find it. If you wouldn't mind, would you send that to me again? Because I have need for something like that.
I will look for it and send it to you.
Thank you very much. Okay, EEPROMs are super easy. The nice thing about P1 projects is that, well, you know, in fact, again, my friend John Huffman has lots of products that use the P1, and in the P1, it uses 32K of EEPROM, but you would always install a 64K EEPROM because that way you could put non-volatile data in the upper 32K, and even if you had to reload the program, that data was protected. So again, we don't quite have that yet with the P, or it's not as easy yet to do that kind of stuff with the P2. We'll get there. All right, finally, unless anybody has any questions on these protocol things, I'm trying to move through fast so we can have fun, because now stuff is going to get real. I almost said a bad word. All right, so this demo runs these pixels. And you can see this is my unified, oops, not that. This is my unified pixel driver for single wire pixels, the asynchronous types. And it has different start methods. So for these guys, I'm using the WS211 driver. I don't have one here close. Those ring LEDs you can get from all over the place. Those generally have WS2812s. Now, this will look, some of you that participated last year were going to say, hey, way to recycle, JonnyMac. Well, you're right, I did. This is a lot of that same code, but heavy but. This code is written in a better way because it's state driven. There are no delays built into this program. Everything is run in a state machine, which is really a better way to go. The reason for this, and I know, again, this seems plotting, but as you'll see, I'm going through and I'm building a small thing. Yep, that works. Building another small thing. Yep, that works. And go building all these things, and then we can ultimately build out a bigger system knowing that's working. The reason I wanted to redo this program as a state machine is that I wanted the ability to be able to interface with the next-gen display in an easier manner. And this allows that. You'll see that shortly. So if we run this program, it gets the similar menu that you saw last year. Notice my lights turned off because it's out. So I have 7 different states of this. Now these have built-in colors. I could pull this down now. So these are my built-in colors. This is a red and this is a whitish color that's not too bright, so that I don't blow things out. So in this case, if I press 1, bing, the lights turn red. You saw that on my face. 2, they turn white. 3 will flash in between them. Now, the flash rate is about 1 second. So, you know, it's slow. The fade, I think, looks nicer. It actually does a morph going between the 2 colors. You probably won't be able to see it on screen. Maybe you can. Here, I'll play Rudolph. You notice the color is changing. So it's doing a morph command in between. Then we have the always popular marquee kind of chase thing. So if I do this, this green screen is just a hassle. But you can see it's chasing around, and then the twinkle. Oh, I was clicking on there like it was an active screen, sorry. And now we get this twinkly effect that we had last year. But you remember last year I had to put, you know, we would actually run out and run the code, and then you have to escape out of that code to get back to the menu. This is running completely differently. In fact, if you look in the program, this is program number 4, the only delay that is in the program is right here. I do this as habit. I have this thing called wait for terminal, because when I'm running a terminal program, if you can see my hands, I press F10, then F12, and then enter to enable. And that will, when I do that, that will clear the screen. So the wait for terminal is waiting for PST and the enter, and then this will clear the screen. And then I just put the 100 millisecond delay in there just to make the screen flash so that I know it changed. So that's just for me to see things. And then this line is drawing this menu. And then here is our state machine. So just running in a repeat loop, this check state method will look to see if we pressed a button to change the state. And then based on our current state, we will run through and do these functions. So the first 3 are actually quite easy. It's we either clear the strip or we set the fixed colors. Then these are time-based states. So those get a little bit more interesting. So let's look in the check state command. Now this again is a keyboard-driven program right now. So the first thing that we do is look to see if we pressed a valid key. In this case, it's going to be 0 to 6 on the number keypad. If it's not one of those, it's nonsense, and we just go back and continue running. The case with state-driven programs like this is you each little thing that you're doing, you want to spend a very small amount of time in it so that you don't get caught out somewhere. Now, if it is a valid state, then what I'm doing here is I'm converting it from a character to a digit, and then I look to see if it's the same as I already have. If it is not a change of state, I abort and get out. Now, if it is a new state, then I would fall through, and so I set my state value to this entry, and I reset my substate, which is used in some of the programs, to 0. And then I start a timer. Now, this isn't a timer object. This is just an internal bit of code that some of you may remember. I kind of harped on Chip last year to put get ms back into the interpreter. And here's why. So I have this timer start. All that I'm doing is I'm grabbing the current milliseconds counter from the P2 and calling that sync. And then I don't use this one yet. I can, but, and then here, if I want to know the millisecond since I started that timer, I call this. It's stupid easy, but gigantically useful. So I'm whenever we change the state, we're going to reset the timer, because some of the things like the flashing and the marquee and all that have time elements built into them. So this is what when I do things like this, I call it an internal object. I actually did just move this code out to an object. I knew that I would. Here's just for the way that I do things. You'll notice that these are all called timer underscore and then a name. So start, adjust. I copied all this out and then got rid of the timer underscore in the external thing. And then in another, this is in another program you see later. Then I just called the object timer. So for the code that I copied from this, it just says timer dot start instead of timer underscore start. So it's if you, again, with a little bit of thinking, I saved myself a bunch of editing. All right. So so now that we're going, there are in the stuff that we're doing today, we're dealing with fixed timing values, so you can adjust them here. So state 3 is the flash between the two colors values. So I'm doing that every second. Now, the next one is called fade, and it has a very short delay. So this is why we want to get on with things. You don't want to wait around too much. It's 8 milliseconds, because what I'm doing is I'm using the morph command in my object. So the morph command takes two colors and it will morph between them based on a phase setting. So the phase setting is a byte, so it's 0 to 255. So if I have a phase of 0, I have these two colors. A phase of 0 means all of this color. If I have a phase of 255, it's all of this color. If the phase is in between, then it's what I'm trying to say, it's a blend of the two colors. That's why I call it morph. So what I'm doing is I wanted that phase, I wanted the change in my LEDs to go from one color to the next color in about 2 seconds. Well, if you divide 2000 milliseconds by 255, then it's about 8 milliseconds. So that's where that is. The next one is the chase timing. And then this is the twinkle timing. And the twinkle will take your color 2 and it will multiply it by, I think I have it set it to from 20 to 100%, or maybe 25 to 50%, and it randomizes it. So you get a nice twinkling effect of whatever you have for color 2. Now, this is a thing that I do often in programs that have displays. Think of it this way: if I was switching into a mode, I'm switching from one state to another one where the first state has a fast time and the second one has a very slow time. I don't want to wait for the timer to get all the way to the end of that new timing condition to do something. So I set a flag called dirty. And what that means is, no, even if the timer hasn't expired, refresh for the new state. That way you get an instant change. In our laser tag products, for example, if you get shot or you shoot somebody, or because you're running out of ammo, every time something happens that could affect the display, I set a flag called dirty so that when you're iterating through the displays, it knows that it needs to refresh them. And this just puts the state on the display. So it's pretty straightforward. And then here's how the code works. Here's the flash, which is pretty easy. So what we're saying here is, if the timer hasn't expired, so the current timer value is less than the delay for this feature, and the dirty flag isn't set, then get out of here. Don't do anything. Just go back to the top of the state and keep checking. If this falls through because the dirty flag is set or the timer has expired, we'll reset the timer, clear the dirty flag. And then in this case, all I'm doing is toggling the substate value. And then here, I'm just setting the strip to either color 0 or color 1. Really super easy. So they would just toggle back and forth. So you'll see the general architecture of all of these are this way. The first thing we do is say, hey, do we need an update here or is the timer expired? And so that's the first thing. So the fade is a little bit more complicated, but you'll see it starts out the same way. Is if the timer is expired or we're dirty, then we're going to run through. If both those conditions are true, we'll leave. Here we're restarting the timer. If in this case, if it's dirty, I reset the phase and direction value. So in this case, I have a couple of variables that are only applied to this method. And so Chip, you know what would be really fun someday is if I could do this. So I could have variables that were static to a method but couldn't be clobbered by the rest of the program.
Oh, okay. Well, yeah, they'd have to, right now
They would be in the external space. They just wouldn't be accessible by anybody else.
yeah, they couldn't be put on the stack because,
Yes,
you know,
you're right.
that's
They couldn't be
dynamic.
stack
So
based.
they'd have to become theirs, I guess.
Yes, they would have, and that's what I'm doing here. It's just that these variables can be seen by the rest of the program. I want to hide them from the rest of the program.
Right.
Not a big critical thing, but I was thinking about that today when I was doing this. So again, you're going to see this same architecture through and through. So this just says, hey, do we need to run now? If yes, we restart the timer. Here, if it's dirty, we know we're starting over. So we reset the phase, which is going to be our morph control. And then the direction, because what I want this to do, just so you're seeing my understanding here, I want phase to go from 0 to 255 and then from back down to 0 and just ping pong back and forth. So that's going to control those fading between colors. So so in this case, phase starts at 0 and ends at 1. I clear the dirty flag, and then each time through, when on our time element, we add the direction into the phase, and then we use the morph feature of the phase to go of the pixel driver to go between color 1 and color 2. So you see that this controls the degree we get on either side. And then this just checks to see if we've hit an endpoint. So if we hit 255, we can only get there coming from 0. We reset the direction to -1. If we hit 0, then we reset the direction 1. Very, very simple. Again, you'll notice all of the code in these modules is very short and sweet and tight, so that we can just be constantly going through the state machine and making sure that we're processing things as we want. The chase is, after thinking about it for a few minutes, it turned out nicely. Again, all this control is the same. So in here, I have a buffer, because what I decided on my chase is I have 4 pixels in a section, and one of them will be lit. And then they're, it's going to look like the pixel is moving. And sometimes people will use 3 pixels, but I found 4 just looked better. You got a natural, you could tell the motion looked better. So we start out by filling that buffer with color 2. So that's our background color. And then we set the element that is defined by substate to color 1. This section will, you notice I've divided the number of pixels in my string by 4. And I have a local variable here called CH, that's for the channel in the string. And what I'm going to do is just move those into the string buffer. So I'm going to grab the buffer and I'm going to move it to the pixel buffer, at this channel, and then just advance the channel pointer. So that'll go all the way through. If you, like in this case, I have 50 pixels. So if I divide that by 4, it's I get 48 on an even value. So this will take care of the last stragglers. And then I update the substate. Now this, I was looking at this and I remember when I'm writing code that is for others to use, I'm always very, very obvious in the way that I do things. And if this was for internal use and I wasn't going to show it to anybody, now this is obvious to me, but here's another way to do that that might be a little faster. You could say substate he was. Because I want to keep substate between 0 and 3. So in a case where if I have a power of 2 number, I will do it this way in internal code. In fact, I was talking about that ADC averaging thing that I was working with John on. I do this because I have an index thing. So just this code and this code does exactly the same thing. This is a little more obvious for newcomers, so just bear that in mind. All right, Twinkle, this behaves the same as last year, just looks nicer, and all I'm doing here is taking color 2. So I will do I'll grab a random value, so it is 25 to 100%. So I grab a random value between 1 and 4. And then I use the scale RGBW feature inside the pixel to take color 2 and multiply it by 64 times whatever this is. That will, and in fact, that will give me brightness levels of 25, 50, 75, or 100% randomly. So this string will twinkle. So it's the same code as last year, just written much more efficiently. So if you put a little, blip on here, you'd see it and put it on a scope, you'd see it screaming through pretty fast because it's not running very much code at any given time. And it always is between every access to any of the states, it's checking to see if there's a change. Now, where is this going to come into play with the NEXTION? Well, remember the NEXTION can send serial messages. So we're going to process those messages in this section so that if we tell the display, hey, do something different, we can process that and get back in. You'll see the framework is, this framework works nicely. But as I was saying to Ken earlier, we don't always have to throw a cog at everything. This, is seeming to do multiple things at the same time because of this state process. And it's fairly simple to set up. Sometimes people will refer to these kind of programs as schedulers because you're kind of going through and doing things on a given schedule. But it's an efficient way to do things. Again, my laser tag project, the whole system runs this way, constantly going through, checking, do I have a radio input? Do I have an infrared input? And then whatever is going on in that particular state, iterating through. And sometimes there are substates in that from displays or sound effects or whatever. And it makes the system easy to manage once you get a handle on the whole state concept. Questions? This has been a quiet group. I'm going to have a drink of water because I'm doing all the talking, which I know people are saying, yeah, you're always talking. Okay, well then let's pop over to the NEXTION. Did I break it? Oh, I unloaded it. That's why.
Yeah, I didn't see it on your taskbar.
Yeah, I was clicking on that blue thing that was
Zoom.
It's the Zoom button, yeah. So. I had all these loaded up, but I couldn't send you the files when I had the NEXTION editor open. So the first thing we'll talk about is, you'll remember this from last week. This is that simple passcode demo, and I'll just run it very quickly. This allows us to put in a code that the thing knows. And send a command, and you saw out here a message that said locked equals 0. If I click on a key, it'll tell me I'm relocked. So very simple. Now, if you look into last week's version of the code, every one of these number buttons has a little chunk of code in there, but it's essentially the same thing. It's saying, hey, this is my key value, now run this handler. Well, in the NEXTION, they have this thing over here called a touch cap. I thought touch cap had something to do with capacitive touch screens. It doesn't. Touch cap is a contraction for touch capture. So what touch capture does, you can see I have one here called TC0. What touch capture does is it grabs the component ID of the last thing that you either clicked or released, and then it has its own events for, for touch, for press and release. So here's the code for the touch cap. What I'm doing is I have a global variable over here called int IDX. So that's what I'm using to grab that value. And so this is grabbing the value of the last thing that was pressed. Now here's where those component IDs become important. So I'm checking here to see if my component ID, which is what this is. So this value that it returns is the component ID of the last thing you clicked or released. And so if it's between 8 and 17, which are the IDs, move my, so if we look over here, if I click on button 9, you see that's ID 17. So this is where there are times when you want to keep your IDs in a specific order. So in this case, these guys that I do the fill in dots, that's IDs 1 and up to ID 7. And then following that, this is ID 8, 9, 10, 11, 12, etc. in ascending order. So when I go back to the touch cap code, again, I grab the value of the last thing, in this case, the last thing I pressed, that's going into IDX. If it's between 8 and 17, which are these buttons, then I'm going to 0 index it by subtracting 8. So now it's going to be between 0 and 9, which matches the digit on the key. Remember, this converts a number into text. I'm going to add it into my entry, and then I'm going to do the check. So in the old version, we had entry.text plus equals, and then I had a fixed string, but I had copied and pasted that into every button. This, if you look here, no code. None of these buttons have code. And not in the press or release. It's all in here because they're doing the same thing. So this is an efficiency thing. I found a calculator demo on tutorial that one of the guys who works with NEXTION did, and it was a very big hex calculator. All of the keys on there had no code in them. There was a touch cap object that took care of looking to see what was pressed and then handled it like this. So it's a neat efficiency. So that's in there. Well, the reason I'm bringing that up is because next week I'm hoping to have a keypad in part of our light control project where we can set the clock from the NEXTION display using a keypad.
So John, show me where you stored the password. I could never find it.
Oh, so there's a variable here called solution, and when we I wonder, can I pull that out? Oh, I can't. When we go into the page, then we set the solution here. Now, if we were talking to the propeller, I would probably send a message at this that told the propeller that I'm ready, and then the propeller could change this by sending a new code that looks like this over its serial link. So here, this is setting the solution, which is the entry code. This is just clearing the, my entry. And then again, when you look at this, we're we're taking the key, converting it to text, and then adding it to the string. And then the check, this thing just checks to see where we are. And if they match, then it will change the heading to unlocked, and it will send this out the serial port. It also changes the locked pick. So we go from locked to unlocked. So there's very little code in this project. It's pretty trim, and it's even more trim now with using the touch cap. So if you're doing things with lots of keys on it, and they're doing essentially the same thing with maybe a small value change, then look at the touch cap to reduce errors and the amount of code you have. Okay, I want to show you really quickly how I did the display for today to encourage you to get artistic with your display. So I'm using Inkscape to do my NEXTION panels. So this is, I'm doing it set, and I should set that in pixel mode. So I click on here, you can see that this is 480 by 320 pixels. But any of you have done, any kind of graphics program or used to layered, programs. So what I have in this, and I do in a lot of things, that I have this faux aluminum texture that I like. John likes it too, so we've been using that on our projects. And then what I did is I wanted to be able to tint that, so I threw in a background color that is transparent, or translucent rather. Here are the controls that are dropped on top of that. Now the sliders, I'll talk about this in a minute. I wanted to make the sliders on this, I didn't want to have to put red, green, and blue text on the thing, since this is a lighting thing. So these are very simple little, there's nothing to these objects. There's a background and then a highlight and a shadow, but I made it so that it looks a little bit dimensional. And so these match the width of the slider object that is in my NEXTION project. So I have 3 sliders here, and then I have another one here, and then I did that pip there. And then these are going to be my color samples. And so I just have a black to start there. But the great thing about this is sometimes moving around the objects in the NEXTION display can be a little tricky. So by doing it in Inkscape or another graphics program that can do things at the pixel level, now, for example, I know that the X is 352, the Y is 22, and it's 106 by 22. And I use that. There's a command called fill that we're going to be using, and I need those values. So the reason I like Inkscape is because it's just a little easier to muscle things around and then do these artistic kind of things. Now, you saw there are radio buttons, and then here's the text for those. I decided to put the text on this because I'm not going to change it. You can make it more generic by leaving that off and then having text fields in your NEXTION, and so you can change them out as you wanted. And then remember, we're going to be treating these like radio buttons. So we need 2 images. We need an image with everything off, and then we need an image with everything on that could be on, and that's what this image is. So you see these all light up. And then we use the crop tool to decide which one of these is on. So it's really, really clean and straightforward. Now, I often will do this too. I'll throw in a layer. This is for my use. I'll say, hey, this is where I want things to be, so that, again, I can click on a, sorry, I have that locked. No, I can click on one of these yellow things, and it will tell me the XY coordinates of where it is. So I can more carefully position things in here. This is an easier tool to use, and then just translate that data over into the NEXTION editor. So this is my approach to creating screens for NEXTION. So now we'll look at the So that those graphics you just saw, this is the controller that we're going to use. This is going to be the meat of our pixel control code. So there we are. Now it sends out serial messages to tell you what's going on. So when it starts up, it says, hey, I'm in state number 1. Now, and so that's changing color number 1. So if I slide this red guy up, green guy up, so I can create a blended color. And when I click color 2, since it's currently black, it will reset the sliders to that and go back. Now you notice when I go back and forth, it goes. So as you look through the code, you'll notice that whenever I change one of the colors, I save it as a 32-bit value that matches what the propeller wants to use for the pixels. And then I do a fill of this, because remember the NEXTION uses 565 16-bit color. So I will take the RGB values that I have and make that. So it's a pretty close approximation. I was running this today and it's pretty good. And so you'll notice here, anytime I change the state, I'm getting a state command and then I have a delay. We won't be using this today. I could not get that to work, but and why do I not have, oh, that's not working. Maybe that's why. At any rate, we're not going to be using the delay slider today, but we will next week. So this is the code that, so if you download it as Ken and I have into your NEXTION, and then run this final program. So that's this NEXTION pixel controller. Now, big fat warning right here. So if it blows up on you, please don't kill me. It is mostly working. And this was not even supposed to be presented today, but I really wanted you to be able to control the pixels with the touchscreen. So if you look, this is the same loop that I had in the other program. I've just changed it from check state to check command. I'm presetting the state to 0 because that display that I just did on the NEXTION, it doesn't have an off anywhere on there. So for the moment, I've just removed that. We're going to put an off button on another screen next week. And then here is what was check state in the other one. This will go through. So you've seen some of the features this is using from last week when we were looking at, I had a terminal program for the NEXTION, so we could just send data back and forth and watch things live. And so the first, when it comes to this, it looks to see if there's a command message from the NEXTION. If there isn't, or if it was an error message, if it's an error message, this get HMI message will return a negative length. We can just throw those away for the time being. So if there's no message or an error message, we just kick it back. If we do have a message, we're going to parse it. And we have these are destinations. Remember, the way that I do things with the NEXTION mostly is I have some string, an equal sign, and then the value. So if we go back over to the NEXTION display and look here, it says state equals 2, and then there's a carriage return after that. So that's how I'm formatting my NEXTION command messages. I have some command equals some value, carriage return, because that's very easy to parse. And so that's what this does, or sorry, this does. And these are my target buffers for the command string and the value string, because it could be a numeric or a string value. Now, this and the return variable value rather from this is the type. Type 2 means, and I should document this, means, hey, it's a command equals value type command. It's not just a page, just a single word command, which is one thing, or a bogus command. So in this case, I want to make sure I'm saying some entity equals some value in that form. That's what 2 is. Otherwise, so if I don't, you'll notice again with these state machine things, we always look to see if we can escape quickly, if something's not on track. So if we fall through to here, we have a valid structured command. So we're going to convert the command, which is the left side of the equal sign, to an index. Now down in the program, we saw this last week. What I've done is I've changed the code. So here are the commands that this program understands from the NEXTION. It's going to say state equals something, color 1 equals something, color 2 equals something, or delay equals something. That's what we're going to get from the display. Those are the 4 things it understands right now. And so if I have a string that says state equals, then that method is going to return an index of 1. So this is a 1, the initial point is 1. If it's 0, it didn't find it as a command, so it's not a known command. Now then, if it was a state command, and the NEXTION actually filters this, so this is actually redundant code, and I maybe remove this. So if 1, that is the command was state. So we're going to grab the value on, this is the value that is on the right side of the equal sign. And if the state is not equal to that, the current state of the program, then we set that. And then the other 2 that we care about, at least for the moment, are the colors. Now the color gets sent out in hexadecimal. If I come over to the here and I go to color 1 and I move the slider. Oh, sorry, I know what's going on. One of the things that I didn't want is just a flood of values. So I have to enable the timer to send that. I've got a timer in here, and that will allow, you notice how as soon as I did that, I got a couple of messages. When I'm sliding between 0 and 255, I don't need all of those values. So what this will do is it's every 20 milliseconds, it will send whatever the current value is. But you'll notice here, I can't make that any bigger, but hopefully you can see it says color 1 equals $, and then the value. So I'm sending it in a format, in hex format to the machine. Again, remember, we could look at this in a standard, in the program that I included last week. We could look at it just as text, so we could see what's going on. And so in this case, I know that color 1 and color 2 come across as hex. So this method will convert anything on it assumes what's on the left side of the, on the right side of the equal sign is hex, and this will convert that value. And then normally we'd have a change of state coming through here. So this is setting up my values for the different states. Next week, we'll be able to read that slider, that state slider, and change it on the fly. And then just like before, anytime we might have to do an update, then we set the dirty flag. So if we run this, one of the things you'll see is that when you have it on your screen, no matter what condition your screen is in, if you're running this NEXTION code, it'll reset everything to 0. This is kind of a very late addition, but it works better. So down in the setup, after we've started the serial for the NEXTION, I give it 100 milliseconds just so it can be ready to go. And then I have an object in the device called HS, so it's a hotspot reset. When you click on that, it resets all of these sliders to 0, and it sets the delay value to 0, and it sets the state to 1, which is color 1. So that cleans up everything. And then here's a key thing. See, this is what I just did manually over there. This enables the timer, so now I can register the slider events coming back in. So if well, now I am running this program, so I guess I'm not. Oh, I know why I'm not, because I have a menu in here. So let me go back to this. So when you run this program, because it's using the menu so you can see what's happening, just remember you got to light that up. So right now I'm in state 1, which is color 1. So I can't show you on camera, but I'm gonna, hopefully you'll see these LEDs around me. If I push the red slider up, notice how they're going. So I'm controlling them live. Hopefully Ken's able to do that too, because he's got a hookup. And the green button and the blue button. So I'm doing live control of the LED colors with the sliders on the NEXTION screen. Are you doing it? Is it working for you, Ken? Are you?
Yeah, I'm just short
the
on
chaser
hands.
Yep. Yeah, that is the trick. So if I switch to color 2, which is currently black, everything goes off. If I click on flash, then it should flash every second. Fade, it will do that slow fade between the two. You see that kind of slow throbbing deal. Ken was doing the chase. So hopefully you can see that. And then twinkle. And my twinkle's not work. Oh, I know why. My twinkle didn't work because I was using twinkle uses color 2, and I had color 2 set to black. So if I twinkle black, it's always going to be black. And so now it's working. So what are the things, you know, as you have time to sit through this, if you look at where I did the text version of this and the NEXTION version of this, everything runs identically. And I think this is an important aspect of development. It works for me is developing things in a, you know, in a way where, you know, you can use easy input. So we know that once we got all this stuff working, then it was just a matter of replacing how we're changing the state with the NEXTION interface, which we had proved in another program. So I promised Ken I would stop after 2 hours. So I'm going to stop talking and just start listening and answering questions that anybody has.
John, a quick question.
Yes, sir.
If you already answered this, don't do it again, because then I missed it. And it's my fault. I'll go back and watch the video.
No, I'll answer.
How did we, I'm not sure I saw you associating the color button to the slider itself in the NEXTGen.
Oh, that's inside the code. Yeah, we didn't get deeply in there, did I? So we'll look very quickly. So we have the 3 sliders and they have their events here. Sorry, let me move my.
So you generated the images outside of the frame, but then somehow you associated those images to the sliders.
Oh, yes, sorry. I know what you're talking about, Stephen. No, you didn't. Yeah, because this is kind of an advanced, well, not an advanced thing, but it's something that I saw a guy had done it on the internet and I thought, oh, hey, I'm going to do that. So here I have a slider and over here, trying to look, I remember so here was, it says PSTA.
Mm-hmm.
That tells you what it's going to look like. Right now it's set to image. So if I change it to solid, then
It's got the flat.
because I'm looking on the see, that was changing just this button. The picture values are what's doing things. So here it says pick 0 is image 0. Sorry, these figure out how to get rid of my zoom control. So here's pick 0 and pick 1, which are the background images of this.
Mm-hmm.
And here are so there's, you can see ID2 is the red, ID3 is the green, and these are the little thumbnails, you know, for the sliders.
Yes.
And the final one is 5. So for the blue slider, ID4 is so pick 2 is going to be the thumbnail. The background of it is coming from pick 0, which has that, you know, that machining, you know.
Nice. Yes. Okay.
And so those are where you set those things. Now,
So you did end up uploading the images of the buttons themselves as
I did. I uploaded my whole folder. So you have the source SVG file and also the PNG files that I'm using in the project. Now, caveat with the the basic and the displays we're using, you couldn't put, for example, a round button on there with this background because it doesn't, the small displays, they have very small SCM processors on them. They don't understand transparency. Now the intelligent display is the one with the red processor, the red PCB rather, it does, you can have odd shapes. So that's why you'll notice everything here is rectangular. So that it's nice and clean, because I have this, you know, I have this textured background and I have these graticules in there and all that. So if I'll try it. I do have an intelligent display, so I'm going to try it with round sliders or, you know, with a line in them. But even with this very small change, I think it's much more attractive than their generic slider, which is just flat and has these funky background colors. Now, you know, in this guy, it's you know, doing the same thing, but with less effort, because all I had to do is change out the thumbnail, and I made both of the background colors black for that. And so, you know, again, this is I live alone, don't have a lot going on in my life beyond what's sitting here on my desk. I like to do artistic projects with technology. And, you know, Inkscape is a wonderful tool for a whole slew of things. I do all of my, if I have an odd shaped circuit board, I use Inkscape. If I'm doing laser cutting, you know, I'm using Inkscape. And a lot of the services, you know, will accept SVG files directly now. So you don't even have to convert to a DXF or anything like that, which makes it really, really great. In fact, I thought I had one here on my desk. I made a medallion for my friend Emlyn. So this is, I don't know if you see it, this is a stainless steel. It's 1/8 inch stainless steel. And this is her kind of her Star Wars logo. It says M4N. So that's her name is M4N. And it's stainless steel. And I got this for $3. Send them the SVG file. And, you know, they cut it out, laser cut it out of stainless steel. So I made a bunch of them for her for her birthday so she can mark her Star Wars cases and things like that. So, you know, I live in an apartment. I can't cut metal in here. You know, I'm limited to soldering. And so it's nice that all these services, these machining services are accepting that.
John, is that place stateside?
Yes, it's called Send Cut Send.
Oh, okay. You've talked about it before.
Yeah. Yeah, they're I think they're in Oregon. They're on the West Coast. Great service, very nice people, and they can cut, I think, up to a 1/2 inch stainless steel. Yeah. Yeah, again, I don't have a machine shop, and you know, I have access to Rick, but he's very busy with the Mandalorian and those kind of things. Yeah. So on the, I guess I could talk a little bit more about this program. So this is kind of state conditional too. You'll notice on my sliders that I am when I'm making a move on a slider, I check to see if I should actually change that to state. I'm calling it program internally, but it will call this function, which is hidden here, which will take care of making, and that's now, sorry, you can update this. I changed this to 32 bits today, so it match up. But this will do conditional things as well. So you have to be on color 1 to make a change of color 1 with the sliders. You have to be on color 2 to make a change. And if you go between them, it will grab it saves a background color here. You can see color 1 is what I save. And then here in this function, it's called HS show. This is where it will take the sliders and it will convert it into that 565 16-bit. And then here is that fill command. So that'll fill a rectangle here or here, depending on which is selected. So there are some basic graphic commands, fills and lines and circles and that. This I found was a better way to go. In the first time I was experimenting with this, I had a flat button on there and I was changing the button color, and that just seemed inefficient. So as I continue to look through, I mean, even though these are fairly low cost devices, they're really extensive. If you go through their instruction set, there's a lot to it, and we're not using very much of it.
So, John, should I be able to have this working with just my JonnyMac board, the display, and the string of lights? Those three,
Yes.
because you showed that other device.
Yeah, the clock
that's got-
module is not involved in this program.
Okay, that confused
Oh,
me. I
you know
thought
what?
maybe-
Here's the thing, John. So if you don't have that clock module plugged in, go into the setup method and look for, because I pre-built this code for the whole thing. So you'll find start methods for the EEPROM and the RTC. Comment those out because they may be snagging because that thing's not there.
Yeah,
didn't
because
have it.
mine's not working and with just this.
Yeah, go into the setup program and comment those out and retry it. I bet you that's what it's because there's no, it's looking for the I2C line to be pulled high and it's not.
John, I didn't have that hardware installed and I didn't have an issue.
Oh, really?
Yeah. John Huffman, did you upload the display image?
Yes, but I had to change the type because I've got the enhanced version. So I changed that in the HMI software.
Yeah, so for what, sorry, John, to interrupt. For those that are wondering, I had set this up on the basic, but if you have an enhanced, like what John's using, then you can go here in this device button and go to the device and you can change. So here I have it set to basic. So what John did is he clicked on enhanced and then that size and then downloaded it. You do have to do that. When you try to download, if it's compiled for the wrong type, it will get grouchy. Another thing, I don't know if he's here this week. I haven't heard him. He usually participates quite like Carol Moore asked last week, hey, can we get rid of these labels on here? And you can by clicking, there's a hidden button kind of right there, because this looks like it says device ID, but those are actually two buttons. So if you click on ID, it will turn those off. That was a question Carol asked last week, which is good for, I think, for screen grabs, because when you're in edit mode, you can zoom in and then you can turn that off and do a screen grab for documentation.
I have a question.
Yes, sir.
Are you going to get to the point where you do talk about implementing multiple cogs with this or not? I know you said earlier that there was no need for multiple cogs, but that would be nice to see as a good programming example if you did do that.
I can. I had originally had anticipated doing that. So, John, can I talk about the architecture of your project? He walked away from his desk. He told me yes. So, John, is it okay if I tell him how we're doing? Okay, so yeah, see, he just leaned in and gave us a thumbs up. So with John's project, John's project is a camera control system. And so he's live controlling cameras and lenses and a lot of stuff. There's a lot of stuff going on in the foreground. And he designed his NEXTION, his NEXTION setup. He's got 16 or 17 pages. He has a lot of things going on. So what we did was in fact, I'm not going to be giving away any of his trade secrets. Let me just load up that program. So you can use a cog, but you don't have to. Well, I didn't think we had to here. So let me show you how I did it for John, and then then you can
John, while you prep that, I just want
Yeah.
to thank you because I have to go on another activity. So I'm going to pass the host over to Chip.
Okay. Thanks.
Thanks
Ken.
so much.